titration of a weak acid and strong base. First, you're going to do a stoichiometry problem, assume it to run to completion, and then an equilibrium problem. So figure out what you have left after the stoichiometry. Alright, so in this case, we haven't added any NaOH yet, so we just have 50 milliliters of a 0.1 molarity acetic acid solution. So we just have acetic acid. It's going to break down into hydrogen and acetate ion. It's 0.1 molarity. We have 0, 0, so we're just setting up an ice table just like we did in chapter 14. Our Ka was given, it's 1.8 times 10 to the negative fifth. Because the Ka is so small, we can ignore X. So our X or H concentration is 0.0013, pH 2.87. Next, we're going to add 10 milliliters of NaOH. So we react it, NaOH plus our acetic acid, double replacement, we get sodium acetate and water. Since it's reacting, we're going to need moles just like we did previously. So it's a 0.1 molarity solution. We have 10 milliliters of it. So that's 1 millimole. And our 0.05 times 0.1 gives us 5 millimoles. React it. We need molarity. And remember, it's total volume, so that's 10 plus 50 gives us 60 milliliters. And stop and see what you actually have left. We have acetic acid and sodium acetate. Together, those make a buffer. So we can do Henderson-Hasselbalch to find our pH. Make sure you get molarity first, though. So you need to find your pKa. So that's 4.74 plus log of our base, which was 0.0167, over our acid, which was 0.0667. pH then is 4.14. So notice pH is increasing. Next, we're going to add 25 milliliters of NaOH. So our NaOH is still reacting with acetic acid. Can ignore the water. Need our millimoles. 25 times our 0.1 gives us 2.5. And we still have 5 millimoles of acetic acid. React it to completion. Notice that our NaOH amount is half of our acetic acid. So we're halfway to the equivalence point. When that occurs, we have equal concentrations of acid and base. They're the same. Remember that according to our equation, pH equals pKa plus log of base over acid. When they're the same, log of 1 is 0, so pH equals pKa when you're halfway to equivalence. So our pH is our pKa, which is 4.74. So make sure you remember halfway to equivalence, pH equals pKa. Now we're adding 50 milliliters of NaOH. And make sure you write small for this problem. We have 5 millimoles, and 0. So notice we have equal amounts of acid and base, which means we're at the equivalence point. But unlike strong and strong, in this case we're left with sodium acetate, which is the conjugate of a weak acid, meaning we have a weak base. So our pH is not going to be neutral. We need to find the pH of our sodium acetate. So you find your concentration, and you need to find out how much of that sodium acetate is going to break up. So you need to set up an ice table. And because it's a weak base, you're going to need the Kb. So you have your sodium acetate. It's a base, so you need water to react with it. So you get sodium acetate and sodium hydroxide. And you could leave off the sodiums since they're just spectators. We have 0.05 molarity, 0, 0, minus x plus x plus x. So normal weak base equilibrium like in the previous chapter. Remember, you got to get your Kb. So it's 5.56 times 10 to the negative 10th. And when we solve for x, it's going to be our concentration of OH. So that's 5.27 times 10 to the negative 6. So POH is 5.27, which makes our pH 8.72. So we're left with a weak base, so at the equivalence point, our pH is greater than 7. Okay, now we're going to add 60 milliliters of NaOH. So I'm going to try this one, setting it up. You have 6 millimoles and 5 millimoles. So notice we're adding more base than the acid we started with. We have our 1 millimole, 0, and 5. We need concentration, so we're going to divide by total volume, which is 110. And then stop and look at what you have. You have sodium hydroxide, which is a strong base, and sodium acetate, which is a weak base. Remember, anytime you have two of the same thing, one being strong, one being weak, as in this case, only the strong is going to matter. So we don't even care about the sodium acetate. We know that our concentration of NaOH is our concentration of OH. So POH is equal to 2.04. So pH is equal to 11.96. Notice much higher of a pH because all we have is a strong base and a weak base. So after the stoichiometry, always assess the situation. Here is a curve look at where you're starting. You're starting at 3, so it's got to be an acid of some sort. Your equivalence point is above 7, so it's a weak acid. Okay, if the equivalence point was 7, then it would have been a strong acid. So it's a weak acid being titrated by a strong base. It's always being titrated by something strong. The region of max buffering, if you notice, that section of the graph doesn't change very much. It's almost flattened. So that's where the most buffering occurs because we have acid and base there. If our equivalence point is 50 milliliters, then 25, we're at halfway to the equivalence. So that's where pH equaled pKa. Other important things to label is at the very beginning of the graph, you only have the weak acid present because we haven't added anything else. From the equivalence point on, the only thing that's affecting our pH is our strong base. You should also know that at the equivalence point, you only have the conjugate of what you started with, which in this case is a weak base. Alright, so most of the time you're not going to have a series of problems like you did. You're just going to have a couple of them. So it says, calculate the pH after we've added 8 milliliters of a 0.1 molarity sodium hydroxide solution. So try that one and then start it once you've got it. We can ignore our water. We need moles. So 0.05 times 0.1 gives us 5 millimoles. And 8 times 0.1 gives us 0.8 millimoles. So earlier it should have been 50 times 0.1. So we have 4.2, 0, and 0.8 millimoles. Divide by total volume, which is 50 plus 8, which is 58 milliliters. So we have 0.0138 and 0.0724. Look and see what you have. We have HCN and NaCN. Together, that's a buffer. So pH equals pKa plus log of base over acid. So 9.21 plus log of 0.0138 over 0.0724. So pH is 8.49. Okay, go ahead and try B on your own. When you're at the halfway equivalence point. If we're at the halfway point, then you need to remember that pH has to equal pKa. If you didn't remember that, you could have solved it all out, but it would have been a lot more work. So 9.21. At the equivalence point, we're going to have our HCN reacting with NaOH. And our acid, we have 5 millimoles of our acid. We can't change that because that's how much was in our flask. Which means we also have 5 millimoles of NaOH because it's equivalent. So we have 0, 0, and 5 millimoles. We've got to divide that by total volume though. We know how much acid we had. We had 50 milliliters. Base, we need to figure out how much base we started with. So because it was a 0.1 molarity solution, and we know that we had 5 millimoles, we can work backwards, get our volume. So we must have added 50 milliliters of base. So 50 and 50 gives us 100. That's where we got the 100 from. So although they didn't tell you how much volume you added, you could figure it out. So we have 0.05 molarity sodium cyanide. Evaluate, we have a weak base, which means we need to do a weak base dissociation problem. It's a base, so we got to react it with water. I left off the sodium. You could have left it. Do your ice table. Remember that you need the Kb. They gave you a Ka, but we don't have HCN, we don't have an acid, we have a base. So the Kb is 1.61 times 10 to the negative fifth. When we solve for x, x is going to be our concentration of OH since it's a base, which is 8.98 times 10 to the negative fourth. POH 3.05. pH 10.95. Go ahead and try this one and restart the iPod when you think you have it. Okay, the answer you should have got was 1 times 10 to the negative 6. If you didn't, we have an unknown acid, so we're just going to use HA. NaOH goes to NaA. We had 2 millimoles and 1 millimole because it says, because that's what they gave us. Notice we're halfway to equivalence then. And halfway to the equivalence point, we know pH equals pKa. We know the pH, so then we can find our Ka. And that's how you get 1 times 10 to the negative 6.